A laser also amplifies light. But surely it does not require an input coherent source of light for its operation. So how does it work then? It amplifies light, yet it does not require an input source for its amplification, for its operation. Well, to understand this, we must first know what is a cavity. You see, a very simple optical cavity is formed when two very high reflectivity mirrors are placed parallel to each other. Let us consider the case of a typical cavity for which both mirrors have 95% reflectivity, and we shine this cavity by beam of light of power, say 1 watt. Now, this 1 watt, the front mirror is going to reflect 95% back. Therefore, only 5% of this 1 watt, that is 50 milliwatt, is what would get inside the cavity. And of this 50 milliwatt, the back mirror would again reflect 95% back. Therefore, you yourself can work out and see that the cavity would hardly transmit anything of this incident light to its other side. Fortunately, this is not always true. Hence, the cavity would have lost all its importance in the context of a laser. A very simple experiment would make the cavity reveal its deepest secret. For this, let us derive this beam of light from a tunable source. You see, a tunable light source is one that gives off light of continuously changing wavelength. And in order to monitor the transmission of this cavity as a function of the wavelength of this incident light, we place a detector on the other side of the cavity and monitor its transmission. The result of this experiment has been captured in this picture. You would see that for most of the, quite expectedly, for most of the wavelengths, the cavity hardly transmits anything, nearly 0 watt. But what is intriguing is that at certain discrete wavelengths, the cavity transmits almost whatever is incident on it, the entire 1 watt. For this discrete wavelengths, the cavity is said to be on resonance. Thus, a resonant cavity is one that transmits, that whatever shines onto it, the entire 100%. While a non-resonant cavity is one that reflects everything that is incident on it almost. On closer examination, it should be seen that only those wavelengths, half of which times an integer fits exactly inside the cavity, are actually resonant to the cavity. Therefore, the resonant equation can be mathematically expressed as n into lambda by 2 equal to L, where n is an integer, lambda is the wavelength, and n is the length of the cavity. In terms of frequency, this equation can be rewritten as mu n equal to nc by 2l, where c is velocity of light. These discrete frequencies, which can oscillate back and forth inside the cavity without decaying, are called cavity modes. And the spacing between the adjacent cavity modes, which is also called free spectral range of the cavity, can be readily shown from this equation to be inversely proportional to the cavity length. An obvious analogy is Bohr's orbits of electrons. As you know, electron can oscillate only in those orbits without radiating, into which its d w wavelength fits an integral number of times. You may be still wondering, so what? Even if there is a resonance, the front mirror is still going to reflect 95% of whatever is incident on it. How come, therefore, everything gets to the other side in the first place? Well, this can be understood by referring to this point. You see, intracavity photon flux, that is the density of photons present inside the cavity, initially is 0. Now we shine this cavity by beam of continuous light at a resonating wavelength. Therefore, the tiny fraction of light that gets inside the cavity will continue to oscillate back and forth inside it because it is resonant to this. Until and unless an equilibrium condition is attained, which in this particular case occurs at an intracavity pod level of 20 watt, because you see 5% of 20 watt is 1 watt. Therefore, in the equilibrium, the cavity transmits 1 watt as its output, while the same 1 watt is also incident on the cavity as its input. And the cavity all the while maintains the intracavity pod at the level of 20 watt. By now you probably would have figured out as to what role cavity plays in the operation of the laser. You say you have an active medium, that is a medium in which you have inverted population between two energy levels, and you place this active medium inside a cavity. Now, as you know, an atom or molecule can only spend finite amount of time in the excited state, and therefore energy levels are actually broadened in frequency as a consequence of Heisenberg's uncertainty principle. Therefore, the gain that you have created between two energy levels does not occur on a single frequency. Instead, the gain is spread over numerous frequencies as shown in here. Now you see, there is gain in all these frequencies. Does it mean that lasing would occur on all these frequencies? The answer is an emphatic no. Lasing would occur only on those frequencies which can oscillate back and forth inside the cavity. The resonant frequencies, and those are cavity modes, and all these discrete frequencies shown here are actually cavity modes. And you see, all these cavity modes have gain, small or big. Does it mean that the laser would occur on all these cavity modes? The answer is once again no. Laser would occur only on those cavity modes which have a net gain. But to understand this, let us go a bit deeper. You see, in a typical laser, reflectivity of the mirror is maintained at 100%, meaning no photon can leak or pass through this mirror, while a small transmission loss is provided to the other mirror, through which the laser beam is coupled out as the useful output. Now, if this loss is independent of the frequency of laser, then it can be readily represented by a straight line parallel to the frequency axis in this gain curve. Lasing would be possible only on those cavity modes which have net gain, meaning whose gain actually exceeds the loss. Now you can see in this example, there are 1, 2, 3, 4, 5 modes for which gain exceeds loss. And therefore, lasing will be affected only on these 5 cavity modes. And the emission feature of the laser would look somewhat like this. The mode with higher gain also will give out higher power. This axis is of course power, and this axis is frequency. Not very monochromatic, you may begin to wonder. True, in order to make the emission more monochromatic, its emission width must be reduced. This can be achieved in one of the two following ways. First, the broadening of the gain can be reduced so much so that only one cavity mode, in this case we say only this mode, has gain exceeding loss, and therefore lasing will be affected only on this central mode, and thus the emission of the laser will be highly monochromatic, because it now basically is a single mode laser. Same also can be achieved simply by reducing the length of the cavity, as then the cavity modes are pushed away from each other, and so much so that once again just one mode sees net gain, and thus lasing would once again be affected on single mode. However, in both this approach, I will go into so much of detail. The monochromaticity is attained at the expense of the operating efficiency of the laser. Same also can be achieved simply by placing a dispersive element, such as a prism. You know that the prism actually splits frequencies. So the prism, what it does, it actually spatially splits the cavity modes, thereby allowing at a time only one of the cavity modes to fall normally on the output mirror. Therefore, only this mode itself can oscillate back and forth and continue to extract energy from the active medium, which is continuously being pumped towards maintaining population inversion. Thus, you see, the cavity not only gives laser its directionality, but also makes its emission more monochromatic. Incidentally, however, the first laser that Lyman operated did not make use of any cavity. You may be wondering, so what trick did Lyman play that allowed him complete dispensation of a cavity? Well, let me digress here a little to tell you the story that goes behind the first experimental demonstration of amplification of light by stimulated emission of radiation. We said the paper that Lyman wrote to report the first operation of laser contained just few illustrations and an extremely short text. It appeared that Lyman did the experiment in the morning, wrote the paper in the afternoon, and dashed it off to the editorial office of Physical Review later before the end of the day. Such an urgency stems from the fact that at that point of time, many laboratories in the world were working hard toward achieving the first experimental demonstration of amplification of light by stimulated emission of radiation. However, the editor of Physical Review later was not impressed. He felt But the data presented by Neyman in his paper was too scanty to warrant publication in a journal of the repute of physical regulation. He therefore took a unilateral decision and rejected the paper, a decision for which he has to depend very soon. The paper then crossed Atlantic and reached the editorial office of Nature. The editor here acted wisely and got the paper published very promptly. That has since been regarded as the first experimental demonstration of amplification of light by stimulated emission of radiation. Well, returning back to science, let us see as to what was the signature of amplification of light by stimulated emission that convinced Neyman to believe that indeed he has operated the first laser. You see, the experimental system used by Neyman was extremely simple. He used a cylindrical ruby rod and optically pumped it by deriving light from a flash lamp which was wound around it. And the ruby then would subsequently fluoresce light at a correspondingly longer wavelength. And the fluorescence will have a spectral weight for the same reason for which gain has a spectral broadening, the so-called Heisenberg's uncertainty principle. Neyman basically wanted to study the fluorescence as a function of the wavelength, and he placed a detector to monitor the fluorescence at one end of the ruby rod, and he basically studied three cases. In the first case, he pumped his ruby very softly, and the spectral width of the fluorescence matched the known fluorescence width of ruby absolutely fine. In the second case, he increased the intensity of pumping, but still not good enough to create population inversion along the ruby rod. In this case, although the fluorescence exhibited a rise of intensity in accordance with increased intensity of pumping, but the spectral width of the fluorescence was invariant. It was just same as before. In the third case, Neyman pumped his ruby very hard, so hard that it created population